Okay, so hello. So we're back, and we're now starting to we continue with our discussion of dimensionless numbers in fluid dynamics. Before going on, I thought I would clarify a little bit about a small point that I didn't quite address properly in the last bit. So there I introduced this quantity mu was the coefficient of viscosity, and I introduced this quantity called nu, right? And I was wondering about the dimensions of nu, right? The dimensions of this are just grams per centimeter cubed, right? So now one way to easily say this is, you remember towards the end of our discussion we said that the Reynolds number which is often given the symbol Re is defined by a characteristic velocity times a characteristic length divided by nu. And from this we can immediately figure out what are the dimensions of nu. Well, the dimensions of nu have to be the dimensions of v, which are something like centimeter per second, times the dimensions of length, which are centimeter. In other words, centimeter squared per second. Those are the dimensions of nu. Okay, simple enough. And therefore, the dimensions of mu are something like gram centimeter second, right? Because it's nu, which is centimeter squared per second, times rho, which is gram per centimeter minus 3. So therefore, this would be something like centimeter minus 1, sorry. So the dimensions of this would be gram centimeter minus 1 second minus 1. Those are the dimensions of mu. So if the terminology often confuses you, both this and that are often called the coefficient of dynamic viscosity. Sometimes depends upon what the author is saying. You can simply figure it out from the dimensions. What are they talking about? Are they talking about mu, or are they talking about nu? We've mostly been talking about mu, but in our discussions of Reynolds number, it's more convenient to start talking about nu, and which is why I introduced this new thing, right? So okay, moving ahead. No, that's not what I wanted to bring up. So let's talk a little bit more about the Reynolds number, which is arguably one of the most important dimensionless number for astrophysics. And as we said earlier, it's given by the ratio of the inertial term to the viscous term. So essentially, this tells you whether or not viscosity is important. That's one way of looking at it. If the Reynolds number is high, viscosity is relatively unimportant. If the Reynolds number is low, so high Re, viscosity is relatively unimportant, right? And vice versa. Okay, low Re, viscous effects are important. So these are the regimes. Now you might ask, unless you give me, is one thing to figure out the characteristic velocity and the characteristic length scale. Those are things that we can figure out fairly easily. But unless you give me this very important transport coefficient nu, I cannot figure out what the Reynolds number is, right? And you would be right. You need to know what the nu is, and in astrophysics, unfortunately, you don't know what nu is. Okay, in several situations, you don't know enough about the microphysics so that you cannot make a statement about nu. This is unfortunate but true. So we go on and start talking about high Reynolds number flows and so on and so forth without really knowing what the transport coefficient nu is in that particular situation. Because astrophysical fluids are very, very different. and they're often collisionless, they're very, very thin, so one cannot make a ready jump from lab situations to astrophysical situations by way of these transport coefficients, by way of these very important transport coefficients. So this is something to keep in mind. Although we might blithely talk about high Reynolds number flows and so on and so forth, we have to be careful. We have to keep in mind that we really don't know what is the origin of this high Reynolds number. Okay, so the other thing is that when at low Reynolds numbers, the flows are generally laminar flows. In other words, as the name implies, the flows, the streamlines of the flows are relatively irregular and they're laminar. And the opposite is the case for high Reynolds number. For high Reynolds numbers, the flows are generally turbulent flows. Okay, in other words, as your intuition would tell you, if you consider, if you think about a streamline of a flow in a given situation, you would expect it to be all tangled. You open your kitchen sink, you open your tap in your kitchen sink with relatively gently. Of course, assuming that the nozzle of your tap is smooth and so on and so forth. So when you open the tap gently, your V's are relatively low, okay, and the nu is just given. Whatever it is for bulk flow of water, you cannot change it. It's not within your control. And there's a certain length scale, say, say the distance between, the edge of your tap and the sink. That would be a length scale. Say half of it is okay, but certainly not 1/10 of it, and certainly not 100 times that. Okay, so when V is low, you will notice that the flow is relatively laminar, is relatively well behaved. Okay, so that would be a low Reynolds number flow. However, when you turn the tap on high, right, so you are increasing the speed and Reynolds number becomes large, and from everyday experience that the flow becomes unsteady and all tangled up. You can see without resorting to very quantitative definitions, you can see from everyday experience that the flow has become turbulent, right? So here is an everyday example of the manner in which the Reynolds number manifests itself. Okay, low Reynolds number, viscous effects are important. That's one way of putting it. But in everyday experience, you can see that the flow is laminar when the velocity is relatively low, so that the Reynolds number is also relatively low. But you can increase the velocity by increasing, by turning the tap on higher, and you can see that the flow transitions to a turbulent flow, right? So here is one practical, example of Reynolds number. The next dimensionless number we introduced was the Mach number, which generally denoted by a script m, which is the ratio of, I shouldn't use this V, something like this, yeah, ratio of flow speed, or to be really correct, we should say some sort of characteristic speed in the flow, okay, to sound speed. And as we will figure out a little later, the speed of sound is essentially the one characteristic speed at which small pressure disturbances travel. I clap, or I'm talking, and the sound is reaching the microphone, or if I was in a classroom, the sound would reach the student, and there is only one characteristic speed, and that depends only on the temperature of this room. Sometimes the density, but if you're talking about isothermal waves, it would depend only on the temperature, and there is only one characteristic speed. Okay, it does not matter whether I'm talking loudly or softly, whether my voice is low or high. Okay, whether I'm a man or a woman, which generally speaking, it determines the pitch and tone of my voice, or this frequency at which I speak. It does not matter. the speed of sound is always the same, and the speed of sound is the characteristic speed at which small pressure disturbances travel. We will illustrate this. I'm simply telling you the definition at this point. We will illustrate this in some more detail as we go along. Okay, so that's the speed of sound, and the Mach number is the ratio of the flow speed to the sound speed. Okay, what can you say? I'm sure you've heard of supersonic jets or supersonic flows, airplanes flying at supersonic speeds, and these are characterized by a Mach number. The plane is flying at Mach 2 or Mach 10. That essentially tells you that it's flying at 10 times the sound speed, the local sound speed, wherever it's flying, or 2 times the sound speed, so on and so forth. Okay, so that's what the Mach number tells you, and you recall the Mach number is essentially the ratio of the first term in the Navier-Stokes equation to the third term, the viscous term. Okay, so that's essentially what the Mach number is telling you, and right. I beg your pardon, I said something wrong, and here was the definition. So the first term to the second term, not the viscous term, the inertial term to the pressure gradient term. This is what the Mach number is, and that turns out to be the square of the Mach number, and the square of the Mach number is v squared over cs squared. So, so that's what it is. And generally, low Mach number, and we will justify this later. Low Mach number situations essentially means that the pressure gradient term is more important than the inertial term, because that's what the ratio is. And low Mach number situations can be considered to be hydrostatic. In other words, the inertial term is not that important, so the flow can be almost to a good degree, depending upon how low the Mach number is, of course, can be considered to be hydrostatic, even though there's a flow. Okay, so here's a very concrete example of how one can simplify things. Right, a hydrostatic situation is much easier to solve for than a hydrodynamic situation. And when can you approximate, even though there's a flow, when can you approximate the flow to be hydrostatic? Well, when the Mach number is low. Okay, another thing one can approximate is another simplification that occurs in a low Mach number situation is that the flow can be considered to be incompressible if the Mach number is low. Okay, so and if you recall, incompressibility essentially means the divergence of V is equal to 0. Technically, these are what incompressible flows. This is the definition of incompressible flow. Perfectly incompressible flow. But the flow does not have to be perfectly incompressible. It can be incompressible to a good approximation. How good the approximation is dependent on the magnitude of the Mach number. The Mach number is, say, 0.1 or 0.05, then incompressibility is a very good approximation. So this is the practical utility of low Mach number flows can be considered hydrostatic and incompressible. Okay. On the other hand, high Mach number flows are, we will explain what this means a little later, can be considered to be ballistic. In other words, the inertial term is what's more important. The pressure gradient term is not important at all. Say if the Mach number is 10 or 100 or something like that. So it's almost as if the flow is like a bullet. Okay, it's ballistic. The gradient of pressure doesn't matter that much. Okay, and such flows are also susceptible to the formation of discontinuities. We will talk about this in some details later on, but such flows are often susceptible to discontinuities that are called shocks. Technically speaking, shocks are places where there's a transition from a supersonic flow, which is a high Mach number flow, to a subsonic flow, which is a low Mach number flow. We will see all this as we go along, but I just wanted to lay a couple of things out. In astrophysics, we will not only be dealing with neutral fluids, we will also be dealing with magnetized fluids. where the fluid carries a magnetic field or the fluid is flowing in the presence of a magnetic field. So, we will discuss the subject of magnetohydrodynamics very briefly, but before that I figured in the spirit of listing out a few important dimensionless numbers, I would say the following also. There is something called a very important dimensionless number, that is called the plasma beta, which is defined as P over 8 pi. It's essentially gas pressure over magnetic pressure. So, and the gas pressure is simply your usual P equals nKT, right. Magnetic pressure is something that we have not yet encountered. We will do so, and I will reintroduce this when we do so, but for the time being this is yet another important, I just wanted to list out this other important dimensionless number in magnetohydrodynamics, not in hydrodynamics, but nonetheless. Obviously, when the plasma beta is low, it means the magnetic pressure dominates over gas pressure. In other words, the dynamics of the fluid will be predominantly governed by the effects of the magnetic field. Okay, what do I really mean by magnetic pressure? Roughly speaking, magnetic field lines behave like rubber bands. A rubber band is a very good analogy for a magnetic field line. Just like you try to stretch a rubber band, this affords tension. Similarly, a magnetic field line, you try to stretch a magnetic field line, this, even though magnetic field lines are fictitious quantities, it's very useful to think in terms of magnetic field lines. You stretch a magnetic field line and you feel a tension. Okay. The other thing is, just like a collection of rubber bands, you try to squeeze a collection of rubber bands and there's a certain elasticity associated with that. Similarly, a bundle of magnetic field lines, you try to squeeze it and there's a certain elasticity associated with it. So, yeah, I'm not giving you all the details. We will encounter that as we go along, but just like the analogy between magnetic fields and rubber bands is a very good one. Hence, you can sort of, if not completely understand, you can kind of begin to appreciate the concept of magnetic pressure. Okay, and the ratio of of gas pressure to magnetic pressure is called the plasma beta. This is yet another very important dimensionless number in magnetohydrodynamics. Okay. And talking about situations where magnetic fields are important, we have already defined the Reynolds number. I'll write this down again. Re was VL over nu, where nu is the viscosity coefficient, right? There is something called a magnetic Reynolds number. Also dimensionless, all of these are dimensionless, right, which is generally denoted by Rm, and this is defined by VL over eta, where eta is the magnetic. So, this you can see is the same as this magnetic diffusivity. Okay. What this is, in order to understand magnetic diffusivity, it's useful to think of the following situation. In a high conductivity medium, you introduce a magnetic field due to some reason. Okay, it just stays there. Because of the high conductivity, it just stays there. Okay. In a low conductivity medium, on the other hand, in other words, a medium which is relatively more resistive, yeah, you introduce a magnetic field, it does not stay there, it does not stay there for a long time, it diffuses away. Okay. And the coefficient of diffusivity is called the magnetic diffusivity. In practical terms, what does Rm tell you? Well, Rm essentially tells you a high magnetic Reynolds number flow is one where the magnetic field is strongly coupled to the flow. Okay. There is a flow and the magnetic field is strongly coupled. In other words, the magnetic field goes along with the flow. Okay, and this is slightly different from what we talked about earlier, the plasma beta. Okay, this is slightly different. In this situation, high magnetic Reynolds number situation is one where the magnetic field is strongly coupled. In other words, the magnetic field, for instance, think of an analogy where the magnetic field is like a piece of wool. It's flowing along with the flow, and the flow takes a turn. The piece of wool also does that. It obeys the flow. Okay, it's strongly coupled. And the opposite situation, a low magnetic Reynolds number situation, is one where the magnetic field is not very strongly coupled to the flow. Just like we talked about the regular Mach number, which you remember was the ratio of the flow velocity to the speed of sound. There's something called, in a magnetic situation, in a magnetohydrodynamic situation, there's something called an Alfven Mach number, which is generally, so you have a subscript A, and this is the ratio of the flow speed to something called the Alfven speed. And what is Alfven speed? I'll tell you in a minute. Again, we will talk about this in some more detail as we come along, as we go along the course. The Alfven speed is just like the sound speed is a characteristic speed at which pressure disturbances travel in a medium, small pressure disturbances, not large ones like a bomb explosion. Okay, small pressure disturbances. Similarly, the Alfven speed is a characteristic speed at which transverse, consider a magnetic field line like so, you twang it, you introduce this kind of a transverse perturbation on it, that results in the magnetic field line doing this, okay, much like a guitar string, for instance, and a wave travels like that, and the speed at which this wave travels is the Alfven speed. Okay, so there's a characteristic speed which depends on the magnitude of the magnetic field and the density of the medium. Okay, and so this is another, just like the sound speed is a characteristic speed in a gas, in a non-magnetized gas, the Alfven speed is one characteristic speed. There are other characteristic speeds as well, but the Alfven speed is one characteristic speed in a magnetized gas, and that's what it is. And the Alfven Mach number is a ratio of the flow speed to the Alfven speed. Okay. In addition, let me give you a laundry list of some other dimensionless numbers in fluid mechanics. One is one important one is what's called the Prandl number. Is generally denoted by PR, and it's defined by nu over kappa, where nu is the viscosity coefficient that we've come across earlier, and this is the thermal diffusion coefficient. Okay, so this is essentially viscous diffusion to thermal diffusion. And as before, the significance of this is simply that if the Prandtl number is high, well then viscous terms are more important than thermal terms, if any. In whatever we've done, we've never introduced a thermal diffusion term in our equations. And generally, these things are not terribly important for astrophysics. These are situations like where the Prandtl number crops up are more in engineering situations. But nonetheless, it's important to keep in mind. And vice versa, a low Prandtl number situation is one where thermal effects, diffusion due to thermal effects predominate over diffusion due to viscous effects. And so I think we will stop there. I thought I would give you, without telling you which equations these numbers arise from, simply give you the definitions and give you the physical import of these definitions, just to emphasize the various kinds of dimensionless numbers that exist in fluid mechanics, and I've just given you a small list. There are many others. I urge you to go to standard fluid dynamics books or even Google dimensionless numbers and fluid dynamics. You'll find lots and lots. And the importance of these dimensionless numbers are they're dimensionless, so they're easy to sort of compare. Is the Prandtl number 1 or 2? Is a Mach number 1 or 10? So on and so forth. Yeah, so that's one thing. And the importance of these numbers are that they characterize the flow. For instance, a low Mach number situation is one where the flow can be considered hydrostatic and the flow can be considered incompressible, so on and so forth. That's another advantage of these dimensionless numbers. And finally, of course, from a more basic point of view, it tells you which terms you can throw away. For instance, when I say a low Mach number situation is one which can be considered hydrostatic, so I really don't need the inertial term at all. That's what it's telling me, right? I can simply solve a hydrostatic equation, which is obviously much simpler, okay, and still be reasonably accurate. Even though there is a flow, even though it's not like the situation is strictly hydrostatic, my answer will be pretty good, because I know that the Mach number is fairly low. But in order to do that, I need to know this beforehand. I need to be sure that the Mach number is low. And I say this with an eye on the Reynolds number, which is really the one number that I care most about, the Reynolds number and the magnetic Reynolds number. These are the two numbers that I often care most about. So as I said earlier, often in astrophysics we make this statement that these flows are very high Reynolds number flows. For instance, the solar wind or the entire solar corona is considered to be a very high, definitely the upper solar corona is considered to be a very high Reynolds number situation. But while this is generally accepted to be true, we make these statements without detailed knowledge of the microphysics. Remember, the Reynolds number is V times L over nu. We make this statement that the Reynolds number is high without quite knowing the microphysics of nu, without quite knowing what the nu is. So these are deficiencies that need to be kept in mind.